we will switch gear and talk about the topic we'll cover for the third module, which is computer organization and basic, like really basic computer system. And the reason I said really basic is it's not like what we are going to learn is not exactly computer systems. It's also more of just the CPU world that we are using right now, which is Intel or AMD x86 CPU, right? And how does that part work? When you go to the PCSA class, the class after this course, right? Then you learn more about how does the CPU is built, how does the memory actually works, and things like that, right? So we keep building this background for you. Midterm quiz is sorry, I need to find a way to hide this thing. Okay, WebEx interface kind of annoying. Okay, it's gone. Midterm quiz topics will cover everything up to lecture 9, and it doesn't include lecture 10 and this lecture. Lecture 10 will not be on the final quiz as well, right? But lecture 11 will be. Logistic is this. We will release the quiz around noon on Thursday. You have until 11:59 p.m. on Friday to submit. And that's it. Any questions? Any questions about the logistics? I will be in this WebEx meeting from 2 to 4. Basically, the usual slot. I'll be here to answer any questions. There's no time limit once you press start, right? Meant for 2 hours. It's meant for 2 hours in the afters. I designed it such that I should be able to finish in 45 minutes. And our TA should be able to finish in maybe 1.5 hours or 1 hour 45 minutes. So for you, right, maybe 2.5 hours, you should not. So if you start to use more than 4 hours, something might be wrong, either with the exam or with the way you tackle the questions. There's no time limit once. What's the, I'm trying to understand that last question. There's no time limit once you press. Oh, you meant like when you download the exam, right? Yeah, it's like homework basically. It's like an extensive, like 30 hours homework that you're supposed to get back at 11:59. Do you submit on a skill server? No, you submit your code. Everything will be submitted on Canvas because it is much easier to track your submitted date and time through Canvas. Uh, make sure I'll allow multiple version of submission. So make sure you submit some version before the deadline. And you can feel free to keep working on it and then keep submitting later version until 11:59. All right. No homework this week. Yeah, I will release the homeworks just so that you can get to see the homework. Right. But this homework will be a little bit longer in a sense, not longer in the sense that it's actually long, but I'll give you more time because you have the exam around the corner as well, right? And while I think I'm slightly evil, I'm not like on the I'm crazy side. So you have more time to work on the homework, but you get to see. And the reason behind that is this homework will cover pointers and cover memory allocation. So I really want you to get some practice on that and basically come back on Tuesday with any questions related to the homework. Is that clear? Speed run. Yeah, I'm pretty sure you can speed run both the homework and the midterm. You release a midterm practice. Yes. Actually, please remind me tonight, so that I would do that tomorrow at the latest. because I have a gut feeling I'll crash like tonight because I'm really tired, to be honest. Oh, yeah, don't do that. Don't go right into core dump and seg fault. Not a good idea. It happens, but I think the key, right? The key is how to get out of it. Because I mean, seg fault happen all the time. It's like you look at my code, right? You saw I just happen to have seg fault too. It's possible. You need to know how to identify what line causing basically cause you the seg fault, what would happen, what usually happen to your code, and how to get rid of the situation, right? So that's a proper skill set to have as a programmer, right? The ability to identify where the problem is, the ability to kind of put together some strategy to get out of the problem, and the ability to actually apply the changes to fix it, right? So this one is actually is really fun once you get used to it, right? So the more that's why if you talk to many programmers, actually will statistically love their job. I know that sounds really bad, but yeah, it does happen. It is actually fun. It's like problem solving on the loop. You see new problems, so you keep solving that, right? So it's actually fun. So yeah, so that's the logistic about the midterm, right? Then what should we talk about next? The next thing we need to talk about is, okay, we talk about file, right? And we talk about data, and we talk about physical DRAM where it store binary value, right? It means that your data, right, has to be somehow stored in some binary number slash format, right? So we'll talk about how that's done today because this is what you understand, right? You understand the number, like 10, right? The letter A, right? The string high. This is what you understand. The thing is, right? Pointer option. This is what your computer understand, right? Which means that there has to be some way for the computer to actually understand this part. What do you really mean? How should I process your data, right? So a quick recap on binary number. How can I represent these number in binary? So can someone throw me a number between 0 to 100 and we'll do that conversion. 42. Okay. Now you start to see how your friends are thinking. So how do I convert 42 into a binary number? How should I approach this? Yeah, you keep dividing this by 2 and you get the remainder. So you get 21 divided by 2. You get 10 remainder 0, remainder 0, remainder no, remainder 0 remainder of 1 divided by 2. Again, you get 5. And this is remainder of 0. 5 divided by 2. Again, you get 2. 2 divided by 2, you get 1. So it's 1 0 1 0 1 0. Right? Let's double check. Let's double check. So you basically gather, right? Once you have all these set of remainder, you gather from this 1 0 1 0 1 0. You gather the remainder, but from the last step back to the first step. So that's how you can convert a decimal number to a binary number. And let's double check that. What's 101010 in binary equals to in decimal? How do I do that? This is basically the same as what is 1 multiplied by 2 to the something, right? 2 to the something plus 1 multiplied by 0, right? Multiplied by 2 to the, so this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, right? So this 1 multiplied by 2 to the 5, 0 multiplied by 2 to the 4, plus 1 multiplied by 2 to the 3, plus 0 multiplied by 2 to the 2, plus 1 multiplied by 2 to the 1, plus 0 multiplied by 2 to the 0. So that's basically 32 plus 8 plus 2. So that's 42, right? So that's how you can convert binary to decimal and decimal back to binary. Any questions so far? Any questions so far? All right, awesome. Hopefully this is clear. If this is not clear, I would definitely ping me. We can do more practice afterward, but I hope this part is clear. Basically, it's just conversion from decimal to binary and from binary back to decimal, right? How about hex and back? Hexadecimal to binary. So let's say I have hexadecimal beef. So 0x typically means that the number is in hexadecimal format. So 0x beef is what number in binary? How do I do this conversion? So I'll tell you a good trick, actually. You look at each of these letters, you break them into each group. What's B in binary? What is B in binary? So A is 10, B is 11, right? 11 is 8 plus 2 plus 1. So in binary, 8 plus 2 plus 1. So that's B. E is 1, 1, 1, 0, right? Because it is F minus 1. F is 1, 1, 1, 1. E is going to be 1, 1, 1, 0. F is 1, 1, 1, 1. So that's our binary representation of beef. Yeah. Why does it work? Anyone can anyone explain? Anyone is minor in maths or something that you can explain how does this work? All right, let me put the explanation to the right side here on why does this trick actually work. So let's look at this, right? 0x beef is what? 0x beef is b, right? Multiplied by 16 to what? 0, 1, 2, 3. 16 to the 3, right? Plus e multiplied by 16 to the 2 plus e multiplied by 16 to the 1 plus f multiplied by 16 to the 0. How do I represent 16 with 2 to the something? 2 to the 4, right? It's basically b multiplied by 2 to the 4 to the 3 plus e multiplied by 2 to the 4 to the 2 plus e multiplied by 2 to the 4 to the 1, like plus f multiplied by 2 to the 4 to the 0, right? How many binary value am I going to have with 2 to the 4? 4 digits binary, right? From 0, 0, 0, 0 to 0 to 1, 1, 1, 1. So the digit represented by the letter B will be the leftmost side when you convert everything to binary, right? Followed by the whatever digits represented by E, followed by whatever digits represented by E, again, followed by whatever digits represented by F, right? Because you can literally group these together. This right is the same as 0 1 0 1 0 1 1 plus 1 1 1 0 plus 1 1 1 0, right? Plus 1 1 1 1. It's the same number. Basically, I break down. This is like b multiplied by what? It's actually b multiplied by something in this box, right? And then e multiplied by something in this box, and then e again multiplied by something in this box, and then f multiplied by something in this box. I can put this box to be 2 to the 4 to the 0, right? The second e is what? Is e, this part is e, right? But you multiply by 16, basically, right? Which is 2 to the 4. It's multiplied by 2 to the 4 to the 2 and 2 to the 4 to the 3, right? Because you keep basically shifting the position of your binary number by four blocks at a time. When you shift things by one digit in binary, basically you multiply by 2, right? Why does shifting in one digit in binary is multiplied by 2? Look at number 5, right? 5 is equal to 101. What is 5 multiplied by 2? 5 multiplied by 2 is going to equal to, right? So 101 is basically 2 to the 2 plus 2 to the 0 multiplied by 2 to the 1 plus 2 to the 0, right? 5 multiplied by 2 is 2 to the 2 plus 0 multiplied by 2 to the 1 plus 2 to the 0, everything multiplied by 2. That's going to be 2 to the 3 plus 0 multiplied by 2 to the 2 plus 2 to the 1, right? So this is basically 1 0 1 0. If you add 0 to at the end, it's like multiply everything by 2. So this is how you can, this is not a formal proof in any case, right? I just want to show that you can convert binary into hex and hex back to binary. How do I convert a binary back to hexadecimal number? How do I do that? So let me throw you some random binary number and let's do this conversion. So let's say I have the number 1 1 0 0 1 1 0 1 1 0 1 1 1 1 0 0 1 1. How do I get the hexadecimal number out of this? If you look at how do I convert hex to binary, how do I convert it back to hex? Exactly, right? You would group this into a group of 4. You would group this into a group of 4. So let me use a different ink color. You would group this into a group of 4, right? This. Okay, this part, I can't draw. Why is it doing this? This part, this part, this part, and if I am not too confused with the number, this part. So this is 3, this is F. Trying to right click. And then this is 6, right? And this is 3 again, and it is 3. So this is 0x336f3. So I can always do this, I guess, all day long, but this is the trick that is really, really handy when you convert binary to hex, because in the computer world, a lot of things are going to be represented in binary. A lot of things are also going to be represented in hexadecimal. And that's actually, let's use that binary representation, right? And now talk about how can a human talk to a computer, right? So again, computer cannot really understand any of our command, right? Well, it does, but let's assume this is the case. We can't just say print hello world to the computer and it will print. What do we have to do to actually give them the command to print hello world? you can just print up, right? But you can't just say print something or display something or give me a coffee, right? It won't do that for you because it doesn't really, unless you program, it's gonna be an extensive changes to how you program your computer, right? It will not know how to process your voice or how to process the English language because fundamentally it's just electrical signal. If you think about it, everything becomes electrical signal. And why binary, right? Why binary format? So anyone built your own computer before? Have anyone done that? So have anyone built your own computer before? Okay, not yet. Let's assume that you have to do that at some point. One of the main components that you have to buy is called the power supply. All right, I see some thumbs up for the for the thumbs up, folks. What does the power supply do? You can also guess what does. Yeah, supply power, right? That's where you connect the actual plug, right, from the electrical outlet into your computer, and you supply the power to your computer. So let me ask you this: How many? What's the voltage from your electrical outlet? 220 volts, right? So what would happen if I supply 220 volts directly to your computer? I guess, yeah, overclocking, you can actually overclocking by increasing the voltage, but if you supply 220 volts, you actually basically frying the computer. No, it's not gonna explode. It just will. I think I've done this a few times with like embedded board before. It's not like a supplying 220 volts, but I short circuit things, and you can smell the burning parts. So because basically you supply in too much power that it actually start to heat up and burn component. Uh, but basically they provide the supply, right? Uh, wait, can you overclock a monitor? I don't know. That part I don't know. I never heard of that. Actually, now you're making me curious. Can we? I don't like why? Really? Oh, you basically increase the refresh rate. Ah, I guess that's possible. That would probably burn the LED a little bit quicker, right? Also burn your eyes faster too. Like so, you might need like like the gaming glasses, which then you cut off the LED lights that you just overclock anyway. Enjoy it while it lasts. When you get close to 30 and 40, you're like, okay, I'll turn the LED down. It's like too bright. Um, Definitely recommend you enjoy it when you can. But anyway, so when you have a power supply, right, it's basically give the input voltage. Power supply would change the input voltage typically from 220 or 110, depending on what country you're in, to 12 volt, 5 volt, depending on what component you want to actually connect to, right? That's called the supply voltage. Supply voltage is basically the voltage that are being supplied to your circuitry, right? I know this is not a computer engineering program, but I just want to use this terminology so that you use the correct term basically. So you have the ground. Ground has 0 volts, right? And the supply voltage should be whatever is being dictated by the component specification. So the job of your power supply is to make sure it goes down to the supply voltage, right? And then if you think about it, right? So for those of you who use laptop right now, what are you going to use for the memory in your laptop is called LPDDR DRAM, for example, right? LP stands from low power. That's how we can design your computer so that it lasts much longer when on a laptop, right? It actually draws a lot less power. And one of the trick, lower the supply voltage, right? So imagine this. Imagine you only have the room between 0 volts and 1.5 volts, right? And you have to detect either it's going to be a high value or a low value. So this is basically a number 1, this is number 0, right? You can imagine this get harder and harder and harder as the supply voltage drop. So that's why binary format is nice, because I can just detect whether I have any charges or do I have none, right? 1 or 0. So that's kind of like the concept behind why do we need ones and zero. Is this always the case? It's starting to get to the point that certain components can detect more steps, just not 1 and 0 anymore, like the SSD, right? So anyone has the this MLC SSD? So you know about what is an SSD, right? MLC stands from for multi-level cell. Okay, SSD actually it does gets a little bit more expensive than hard drive. Back in the day, SSD works like DRAM. That one storage element, right? So one storage element store 1 bit, and we call this single level cell. Single level cell. I have one empty space and I will store either 0 or 1, because I can only tell the status of 1 or 0. Cell, that's a great question. I will actually go sidetrack a little bit. So cell, typically we refer to a storage element inside these memory or storage, right? Storage, which can be hard drive or the SSD. Why do we call it a cell? What is a cell? in English, what does a cell? What does the word cell mean? Yeah, right. So you can also refer to this like space, right? That you can store something in, right? For example, a prison cell where you would store put in the prisoner, right? So in this storage and DRAM terminology, whenever you see the word cell, it means the space where you can use to store whatever, like in DRAM, folks, in your DRAM main memory, it store the electrons, it store the charge. If there's electrons, that's a value 1. If there's no electrons, that's a value 0. The reason why I didn't say electron, because for the SSD is use the same word cell, but it, because it's different material, it doesn't actually store electron. It store the status of the material, and you can read the status between 1 and 0. But the MLC, which stand from for multi-level cell, it means that 1 bit can store not 1 bit. One storage element can store one storage element can store something like 0, 0, 0, 1, 1, 0, 1, and 1, which means now I have one storage element storing 2 bits, or 0, 0, 0, 0 0 1 1 0 1 0 0 1 1 1 0 0 1 1 1 0 1 1 1 0 and 1 1 1. I store 8 different patterns, 3 bits, right? For 8 different patterns. Now I have one cell, I can store 3 bits. What's the benefit of this? What's the benefit of this? So if I come up with the SSD that can store 3 bits per cell, with the same number of cell, in the SSD, I can store 3 times the amount. The capacity is 3 times the amount. So that's how you can get a terabyte of SSD, right? This is a really, really common trick in how you produce the SSD. Again, definitely not on the exam, right? But I kind of want you to know the difference between what does multi-level cell mean. Oh, yeah. So this is a great picture. Yes. So you can see the screen, right? Thank you so much from the link. So that's basically this giant box is one cell, but it can store more status as you have the uh, uh, different level of cell. To be honest, MLC is this is actually that's one wrong thing about this figure, right? MLC doesn't mean 2 bits. MLC means more than 1 bit. Usually 2 bits, it's like double level cell as well, like triple level cell, multi-level cell is like, I mean, the word multi, right? It can actually means any number of bits. So sometimes they can refer to TLC and QLC as well, right? QLC is quad level cell. There's also downside that comes with that. QLC would have the SSD in QLC would die sooner than the TLC, and TLC would die sooner than the 2-level cell. There's a reason behind that. I'm not gonna talk about it. But if you buy SSD, these are something that you can take into account. If you want to learn more, stay tuned after class and ask questions. All right. So they don't last as long. There's certain number of writes that you can do to these cells. Imagine this, every time you write new data in, you shock them, right? You shock the cell every time you are writing. So it means that if you shock something more than enough time, it dies. Just think of it that way. It's just some material that gets shocked repeatedly over and over and over. And if you shock them too many times, they die. It's not a biological cell, obviously. It's a material that are not living things. But because when you shock this cell, right, to make sure they change the properties, it like things like heat get generated. It is not. I use that word so that you can see the picture, right? But the reason behind it is because when you write to it, you actually need to supply power inside to change the material property to whatever value you want to write to, right? So this write process, two things, take times, and it actually slowly killing the cell. Yeah. And it's actually a big research problem too, how to make sure this thing lasts longer. It's a huge research problem. And that's why you now can get terabytes of SSD, but without the downside that it actually die really soon, right? It would last 5 years, it would last like easily 8 years. I have an SSD at home that is still like going strong after 10 years. Um, and yeah, so there's quite a lot of things that you can do to make sure that this thing lasts longer. Feel free to let me know if you have any questions about that. Many of my close friends actually do research on this topic, and it's actually pretty fun. Hard drive lasts longer because they use so hard drive would get destroyed with a totally different reason. Hard drive is more mechanical, like you have this disk, right, and it has the pin that go around and read the disk. So hard drive, um usually when they breaks, it's mechanical related. Like the read pins kind of touch the disk and it destroy the disk, for example, or you drop it, or it's just old age. I There's actually a paper that do a survey on uh, how long does hard drives typically last, right? And what you see is we call this a bathtub pattern, which is something like this, right? Sorry, let me use the eraser. Number of hard drive that die age. It's actually something like this. So there's a lot of hard drives that die quickly because it just doesn't pass the QC, right? And many of them would last for about 5 years. So if you have hard drive that is longer than 5 years, consider backing it up. If you've been using for the past 5 years, they might die. Like this, I think this paper gathered from the a lot of drive from data center, uh, and SSD still lasts longer. I do agree. Now that I use both, right? I still have not have any SSD dying on me. While I have two hard drives dying on me already within like 7 years. So that's kind of my own personal verdict. So anyway, anyway. So let's. I mean, you just need to make sure you back things up, right? Make sure you store your data somewhere else if you need to recover things. In codes that are important, put that on GitHub. Those are perfect as well, right? But anyway, computer talks in binary, right? And we can't directly talk to your computer. I'm trying to come back to our material. The idea here is we can talk to the computer by representing our instruction, right? Our instruction, like add, subtract, multiply in binary, so that the command becomes some binary pattern. For example, I can say something like this. Let's assume add is 101101. If you see this pattern, it's adding something. A subtract is 101110. So if you see 101101, computer is trying to add two numbers. If you see 101110, it's trying to subtract, right? This is actually the reality of what's happening in your computer. It keeps reading those patterns that the program represent, right? And then convert to instruction. The data also will be converted to binary. And we use this interface, right, between assembly and make sure that we can program your computer. So let's now talk about the data part, because that's the easier part. We're not going to talk about the command part. We will talk about the command part more extensively in the next course. How does it differentiate between math operation and just pure constant? Great question. If they're all in binary, right? So let's see if I have any room here. Let me write on this slide, right? So if I have a command like add, right, versus constant, right? I can have 101101 as a constant, and I can have the add as a command 101101. How can I tell the difference? That's a great question. So that's the job of computer architect. Actually, this is actually the job of people who work in my field. What we do is we will first write it's called instruction set architecture, or ISA, like x86 assembly. It would actually tell that this is how computer would process each binary pattern that they see. And it was first one thing that you can assume, for example, like this is an example that is true in say RISC-V or ARM, right? Which is they can assume that each instruction is 64 bits or 32 bits. It means that I'm going to read 32 bits and that becomes my instruction, right? And if the instruction contain the constant, there'll be a specific pattern that say, hey, what's coming next are constant. Is it more clear? So for example, if I want to add, right, if I want to do the add a plus 5 versus add a plus b, right? It can be something like 101, 101, and then something that represent a, right? And something that actually represent the number 5, which is this. Yes, that's like a placeholder if you say, right? That is it reads the pattern, and then the add a plus b is going to be slightly different. I can define a separate instruction that if you see 101111, it means I'm adding a and b together. Both of them are add instruction, right? Both of them are trying to add two number, but I tell the difference in the add instruction itself. Let's say, hey, if you see 101101, look out for one variable and one constant that come up later. If I see 101111, look out for two variable. So we would compile, right, a long manual that say, if you see this pattern, look for this. If you see this pattern, look for this. If you see this pattern, look for this. And that we would basically make sure that it's Turing complete and it actually programmable, and hopefully it's convenient to use and powerful. So is it more clear? By the way, great question. This is awesome. Or am I just confusing everyone now? So there'll be like multiple variation of the add command, like add constant with constant, add variable with constant, add variable with variable. We will go through that soon, actually, in like I think 3 lectures. So now let's talk about, so this is actually representing the command, right? But now let's talk about representing the data, because that's a lot easier, right? Because everything in the program involves data. You have data as the input and it should spit out something that's useful, right? As an output. The first thing that we have to talk about, because sometimes the data doesn't take only 1 byte. So we have to talk about the memory organization. The memory organization. What does it really mean is, if I have an address, right? So let's say this is my DRAM. How I am going to access this address? What should be the organization, right? So if you want to assume something that is true, right? Your program will have its own view of the address locations that you own. This is what we discussed earlier when we talk about allocation, malloc, right, with pointers. It's a concept behind a virtual address, which we will cover toward the end of this semester. And if you think about it, this is a contiguous space given to the program. The programmer sees that, and the programmer can use the space. When the program is executed, the compiler and the runtime will control this allocation. They would determine where is the actual location that should be stored inside DRAM. And they'll provide a mapping between the address as you see and the actual physical location of that data inside your DRAM. All right. So the first thing that we have to talk about is the word. in the computer world, right, a word is a unit of data. Why do we say that? So can someone give me the definition of a word in English, in human understandable meaning? What is a word? What is a word in English? It's just, yeah, it's a bunch of character, right, that put together and it means something. It means something. So you can use the same concept in English, and this is actually what I find really nice about a lot of things in computer science, like a lot of definition, because we are not that creative. We just find the closest English word that represent what we are trying to build, right? Um, yeah, let's just picture-based language. That's let's not go there. In a computer, there's also a word. It's a unit of data. Think about it as a word is a unit of data. Typically, if you look at the 64-bit machine, a word is going to be 64 bits. If it's 32-bit machine, it can be 32 bits or 4 bytes, right? So if you buy an Intel CPU or AMD CPU these days, one word is going to be 8 bytes because it's a 64-bit machine. That's what most of the case, right? Whatever is encapsulated in those 8 bytes, it means something. It's a strung together bits of ones and zero that means something, right? And it's a unit in which the hardware can use to transfer the data. It is actually done together as a word, as a unit, right? Different architecture can support finer or coarser data size as well. For example, the GPU can support half word, right? So that you can do like 2 operations in 1 word. Uh, the bus will also allow you to transfer multiple words at once, depending on the design. Basically, these are the design decision. I say I want to optimize certain things. You don't have to go by 1 word is 8 bytes, right? Because you are designing the hardware. Because at the end of the day, everyone are engineer and scientists, we can build our own thing. As long as it works and as long as they perform well, we are good, right? So most of the time a word is a unit of data, but you can have a different architecture that can support finer or coarser data size as well. Memory also is addressed in bytes, right? It tell you the exact byte location. An address typically would point to the first byte of the word. Because an address goes into each byte, but one word is 8 bytes together. So when you give an address, it typically would point to the first byte of the word. For example, right, when you move to the next word, right, you go, if it's a 64-bit machine, you go 8 bytes at a time. If you're in a 32-bit machine, you go 4 bytes at a time. These are still definitions, so hopefully these are clear. In C, you can use %p to print pointer and %x to print hexadecimal number. That's why I said hexadecimal number is really helpful, because when you look at the address, it's a lot more compact and it go by 8 bytes at a time, right? So you can see the increase in the number with the hexadecimal format is really easy to debug. But now this is the part that will confuse most people. Anyone here heard about this terminology? Big versus Little Endian. How many people never heard about this? All right, awesome. So let's say this is my DRAM, right? And I say, how big is one word? How big is one word? How many bytes is a word? Yeah, that's awesome. This is great. So it's 8 bytes, right? 8 bytes. So my question, if my 8 bytes data is let's say it's something like 0000 beef, I'm hungry. keep saying beef. So this is my 8 bytes data, a bunch of 0 and B, E, E, F. Where should I put in the EF? Should I put it into the to the left side here or to the right side here? It depends, actually. Some machine would put it toward the left side. Some machine would put it toward the right side. And that's big versus little endian. All right. So it basically dictates when I have my data, right, in this format, where do I put the bytes of each of these data toward the left side or toward the right side? And this is how it goes. So basically, a byte in a word can be ordered differently across different machine depending on what happened when I designed the machine, right? For example, if you have the big Endian machine like a network protocol do this a lot, or the like computer that come from the company called Sun Microsystem, right? The least significant bytes. So this is going to be the least significant byte. This is the most significant byte. It's going to be at the highest address. So if I have 0000 beef, I say the least significant byte is in the highest address. This is low address. This is high address. So where do I put the EF? Is it toward the right side or toward the left side? I said least significant bytes will be at the highest address. So if I have a big Indian machine, right? What's the significant here? So great question. The word significant, when I put it to the significant bytes, it means that if I look at the value of these 4 bytes combined, which byte will have the most impact on the total number, the total value, right? So in this case, which byte is the least significant? Is E and F, right? The last E and F, because it's just E multiplied by 16 plus F multiplied by 16 to the 0, right? And the first two zeros, those are going to have the most significant to my value, because it's 0 multiplied by 16 to the 8 to the 7 plus 0 multiplied by 16 to the 6. So if I have anything in there, it's going to change the value by a lot. Is it more clear? That's why the bytes to the left will have more significant to the total value of this number. Yes, yes. So the byte toward the left will have more significance, because if you try to convert that to a number, they are gonna be a big factor into, is that gonna be in a million? Is that gonna be in a billion? Or is that gonna be in a tens or 100, right? So that's what we typically meant by significant. All right. So in the big Endian machine, it will be EF will be toward the right. In the little Endian, which is something like an older version of x86 or ARM, right? Nowadays, both x86 and ARM will support both formats. You can kind of use both of them. But in the older version, the least significant bytes will be in the lowest address. So if I am running the program on x86 and I have the number 0000 beef, the EF will be on the left side, or is it on the right side here? On the x86 machine. Would that be on the left side or would it be on the right side? The left side, right? So it's each byte, but one byte are 2 letters in hexadecimal format. So it's EF. That's 1 byte. So the EF will be put together. Yeah. One byte is 16 bits. So it's E and F. Yeah, just want to make sure you not 1 byte is not 16 bits. 1 byte is 8 bits. So it's E and F. And some architecture like the IA64, modern version of ARM, Alpha and MIPS, which is another great sample of the more I guess older architectures that kind of now evolved to the newer architecture like RISC-V will support both formats, right? For example, let's assume I have an address X that has the value hexadecimal 1, 2, 3, 4, 5, 6, 7, 8, right? And the address of X is at 10, right? Let's make that assumption. If I have the Little Endian machine, the location that address 0x10 will store 7, 8, right? Because it's Little Endian, again, Little Endian, least significant bytes, in this case 7, 8, right? This is least significant. This is the most significant. So you could always go with the least significant, and you have Little Endian, lowest address, Big Endian, highest address. So it's just where you put the least significant byte. That's how you can remember it as well. I don't recommend you to remember it. Just go look at Google, look through Google. Just like you don't have to remember that. What you have to remember is different machine can have different format. So be aware of this when you, for example, have to program in the microcontroller. This is one big thing that can happen. Like you try to send in the data 0x1, 2, 3, 4, 5, 6, 7, 8. It reverse that for you because it's a different Endianness. So this can happen, right? So be aware of this organization, little versus big Endian. Any questions? Oh, what's the purpose of each of this, right? So back in the day when the resource are really constrained, right? Sometimes you cannot always transfer those whole thing at once, right? You sometimes you have to transfer 1 byte at a time. So it's a designer choice of like, do I put in the least significant byte first, or do I put in the most significant byte first? So it depends on the application that would get run on these type of system. Sometimes just design time back in the day, right? That can also happen as well, right? Because at the end of the day, engineer have to pick one, so it can happen that way too, right? So many of these, that's why I said many modern architecture would support both formats, but you need to know what format is going at right now so that you know what bytes would have the least significant bits of your data and what address will have the highest bits, right? So hopefully that answered the question a little bit. It's kind of like at before we have a lot of like compute resources, before the bus is like really wide, you can transfer many bytes at the same time. When resources are more constrained, there's a trade-off between what you want to send. There's a trade-off between what you want to send. For example, right, if you have the big Endian machine, right, trying to send things through the network protocol, right, putting in certain bytes first can have the benefit, in terms of data processing, for example, right? So that's why I say it's a historical perspective, because these days we have a lot more resources. And again, you don't have to be honest, you don't have to strictly remember what bytes go to what for big and little endian. Just remember it's least significant bytes, and then big is highest, little is lowest, right? And then how to actually use, what do they actually mean. All right, so now let's move on to the next slide if there's no more questions. For data types, another big topic. Let's start really simple, because we have multiple data types that we cover so far in this class, right? Let's go with character. So how do I represent character? Can someone tell me how do I represent character? Ascii, yes. So it's a format, right, that maps the value between 0 to 255 to a character. So how many bytes do you need per character? Is log up to 56. Log 2 up to 56 is 8 bits. So you need 1 byte for that. Right? Or 8 bits, right? It means that if I have a letter, so what's the ASCII representation of the letter A? Someone tell me that? Capital A is 65. So how do I represent 65 in binary? It is basically 64 plus 1, right? 64 plus 1. So it's 0, 0. In my pen. 0, 1, 0, 0. So that's 65. Now, with this conversion, I can now represent data in a character format from the letter A to binary. Now, I can actually make the computer understand letter A. Right? Now, my computer understand the letter A. If I see the pattern 0, 1, 0, 0, 0, 0, 0, 1, that means it's the letter A. All right. And this table is basically us, human, right? Come up with a table. We just say, if it's the number 65, that's letter A. If it's the number 66, that's letter B, right? If it's number 67, that's capital letter C. I think lowercase a is 97. I forgot actually, but it's like we can now differentiate between lowercase, uppercase, all the letters, all the number, things like a tab, character, a space, or even things like a line break, right? So we can use it to uh, convert your letter that you're typing, right, into number. How about the string? So a string is an array of character. If I know how this character works, string is just an array of character. So this is really simple, right? Each character is encoded in ASCII. The thing that you have to be aware of is if it's an array of character, it has some maximum size, right? So let's say I have char temp 20. How many letters can I store here in temp 20? How many? Up to how many letters? It's actually, so now your answer is yes. So it's 19 plus one noun value at the end. Why do we need noun? Can someone tell me why do we need a noun character? So let's say I want to do something like temp equal cat, right? Temp equal cat. How can I tell that that is just a 3-letter word? There's nothing else afterward. I just want to represent the letter CAT, and that's it. Yes, we put in CAT followed by the value 0, right? This is the value 0. It's a noun character. It tells that that's the end of my word, right? Even though I have a temp of size 20, I need to put this in. So now let me ask you this. I said temp can store 19 character plus 1 noun terminator, right? 19 plus 1 noun terminator. It means that what if I store 20 character? What would happen? And let's say I do printf on temp. If I do printf on temp and I try to fit in all 20 character, will this segfault actually? Have anyone tried to do this without segfaulting? Sometimes it will not segfault, but you get weird symbols, right? Why? So let's say this is your DRAM, right? This is your DRAM. This is the range of temp. Hi cat. Right. Let's say I just say hi cat, and I didn't put in the now character. Temp is only size of 5, and I run printf. What happens afterward? What would printf do? Printf basically go keep letter printing letter by letter by letter by letter until you hit the now character. Did you hit the now character here? No, right? So what will printf do? What will printf do? It continue to the next whatever byte it reads, so it goes here. Whatever character is that, it takes 1 byte and look at the ASCII table. If it's not 0, what will it do next? It would then keep going, right? It would keep going until, let's say this is a bunch of 0 afterward. Let's say this is a bunch of 0 afterward. You go, oh, 0, I've stopped. Now, do you see why if you by accident fit in too many characters, you see weird symbol? Because whatever junk after my temp variable, I don't even know what is the data in there. It just might be some number that represents the weird symbol that you saw, right? And it will keep printing until it hits a bunch of 0. Any questions? I would say that's a bug, not an Easter egg. Easter eggs is intentional things that you put in your code that will probably not harm the program. So the function size of will give you 3 characters. It's not a feature. It's if you do this by accident, I would call that a bug because you're supposed to put in the now character at the end, but your array is too small and it would explode. There was a so you can also scan f into a string, right? Let me put it that way. Let me kind of spin it this way. You can do the scanf in a string. It, yes, no. It's something simple. Scanf. I just do a scanf into the string. So let's say this is my string, right? What if I just put in the input that's way too big? It's too big that it goes into the part where my code resides. So this is your input. What would happen here? So I put an input string, but it's way too long. It doesn't fit within the string. It does actually go over to the point that it go into the actual program. Whatever program is stored on your DRAM. In modern processors, definitely segfault. That like you get protected by that. But if you don't have virtual memory, if you like go back to the old, like really old computer, right? Uh, look up the thing called buffer overflow. It's one way you can kind of hack into a program. You can actually overwrite your function, right? With your own code, you can write your function inside your input string so that it overwrite your program. And you can do it in such a way that once you return from a function call, you don't go back to the original function, but you go and overwrite that already. So it doesn't go back to your original function. It go back to my own function that I just write in, right? Modern computer have a lot of things you can do to protect from this buffer overflow, so you don't have to worry about that. But this thing exists, right? You can actually Wikipedia buffer overflow, and it's actually something pretty neat for you to read. But anyway, so we already go through this example, but let's say I want to have a string called syskill, right? It's basically will be SYSKILL followed by 0. What does it look like in DRAM, right? So basically, what is the letter S? Sorry. It will be the binary for letter S, followed by binary for letter Y, followed by binary for letter S, blah, 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 and then followed by 8 consecutive 0 for binary 0, right? And that's what your DRAM would look like at that location. All right, so that's how you can represent a string. Any question? How about an integer? This should be a lot easier, actually. Integer can be represented using binary value, right? So let's say I have an integer of size 4 bytes. Yes, I can go back to 0.5 seconds. Yes, here. Sure. What's the question? Oh, that's it? Okay. Sorry. So integer is really, really simple. Because we just did an example of how do we convert decimal number into a binary. Same thing here. But with some caveat. I have integer 4 bytes. Let's say I have the integer is 4 bytes. What's the maximum and minimum number I can store in this integer? Because it definitely will have the range of the maximum number within those 4 bytes that I can fit in, right? So how many bits can I store in 4 bytes? How many bits are there in 4 bytes? Each byte is 8 bits, right? So 4 bytes is going to be 32 bits. So if I have 32 bits, I can represent 2 to the 32 different number, right? And let's say I want to represent negative and positive number. What is the minimum number and what's the maximum number here? It's actually negative 2 to the 31 up to 2 to the 31 minus 1. It just we count 0 as a positive number. So it's 2 to the 31 minus 1 plus the 0, and then the rest are the negative number. So that's a range, right? There'll be one sign bit. There'll be one sign bit. The sign bit will tell you is it a positive number or a negative number. If you talk about NCC, sorry, if you talk about NCC, NCC is like when you look at the old textbook on C, right? When you're still talking about 32-bit machine, you have integer that is 2 bytes, short integer is 2 bytes, long integer is 4 bytes, and you can have long, that's 8 bytes. Modern day GCC integer is 4 bytes, as you have already saw from the example, right? And as I said, the size of each data type can change depending on the architecture, depending on the version of GCC, for example. The version of the compiler, right, can change the size because NCC, for example, would go with 2 bytes integer. You should use the size of, put in size of int just to be safe, and you want to make sure that's the case, right? Oh, here. It's just a definition in NCC, right? That there are also some version of C where short integer is actually like 2 bytes and integer is 4 bytes. So that kind of depends on definition of how each version of C define the size of your data. So hopefully it's more clear now. I know it doesn't help, but yeah, that's what it is. So is it more clear? Sure. Yeah, I know. It's kind of like why, right? Do you also have to talk about signed versus unsigned? So can someone tell me what does unsigned mean? There's no negative number, right? So if I have unsigned number, it's 0 to 2 to the 32, obviously. So that's simple, right? 2 to the 32 minus 1, sorry. Integer can be positive or negative. So if I want unsigned format, I can represent, if I have 4 bytes integer, I can represent number from 0 to 2 to the 32 minus 1. Right, so that's unsigned. It's only positive numbers. Signed is interesting in a sense it uses the two complement format. Oh, great question. You can also use signed and unsigned character. You can do that. The caveat is most of the time, if you go with unsigned character, you're treating character as a number between 0 to 255. You typically treat that as 0 to 255. And why do we need this? For example, if you want to represent RGB as a color, right? How many of you are familiar with RGB? So what's the value for R and G and B? What's the range of the value? 0 to 255, right? This is 0 to 255. This is 0 to 255. This is 0 to 255. So do I need 3 integers for this, or do I just need 3 characters? So if I use 3 ints, right, that's 12 bytes. That's a lot. If I use 3 character, it's only 3 bytes, right? So I can save a lot more. I just save 4 times the amount with 3 character, right? So in that case, I think one way to safely use RGB is use unsigned character. Number from 0 to 255, right? So does it answer your question? Basically, you can do signed and unsigned character. So it's just a keyword unsigned means I'm going to treat this as 0 to 255. Actually not sure about that. Let me look it up. Can we get num from UTF format? That's a great question. Yeah, I'm not sure. I'll look it up. So with the signed number is done using what we call two's complement format. This is going to be a new terminology for many of you. What it does is basically the two complement format is actually really simple. So let's say integer is 32 bytes, right? This is my integer. It will treat basically the most significant bit, right? The most significant bit, which is this one, this will be a negative value. The rest as a positive value. This is basically how signed two complements format work. The actual value of this number is you add them together. So let's say my integer is 1 followed by a bunch of 0. 1 0 1, right? This is what a bunch of 0 followed by 101. What's the number? Integer is 4 bytes. It's just I don't have the ability to draw 32 different boxes. Sorry. Because I need to write in 32 bits, which is long. I am lazy. I'm sorry. It's actually, this is not -5. In the two complements format, this number is 5. This number is what? -2 to the 31. So this number is -2 to the 31 plus 5. This is how you compute the value of the signed number in two complements format. You see this bit pattern, you take the last bit, if that one is negative 2 to the 31, and then you add the rest. That becomes the value. That becomes the value that I'm talking about. So basically the value that I'm looking at right now. Y2's complement format. The beauty of the two complements format is, let's say I have the number A, right, in the two complement format. I can get negative A by flip all the bits and add one to it. It's a really, really neat trick. So again, let me continue first. For constant value, you by default it's a signed format. Unless you have the letter U next to the number, that becomes the unsigned constant. But I can convert, for example, number 5 into negative 5 by doing, what's 5 in binary? What's the number 5 in binary? 101, right? So I have the number 5 here. So this is 5, right? If I want negative 5, this is how I can do it. I flip every single bit. So you get 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0. So I flip all the bits, right? And then I add 1 to this. I will guarantee that this is basically negative 5 in two complements format. All right. Any questions? Any questions about this? There's going to be one other small sub task in assignment 4. Do a negative number, return a negative number using some tricks. So you flip all the bits and add 1. So you get the negative number of that. If you have negative 5, if you have a negative 5, what would happen if I flip all the bits and add 1 to it? Let's do that, right? So again, from here, let me put the number here. Negative 5 is 1, 1, 1, 1, 1, 1, 1, right? And then 0, 1, 0 plus 1 is basically 0, 1, 1, right? This is negative 5. I flip all the bits. I'm going to get a bunch of 0, right? 1, 0, 0. And you add 1 to that. It becomes a bunch of 0, 101. This is actually number 5. See? So you can flip from positive to a negative number really in a really, really convenient way in the two complements format. All right. What would happen if you mix the two? If you have signed plus unsigned, right? What would happen is, let's say if I have A plus B, but B is signed and A is unsigned. What would happen is, in this A plus B, B will be converted to an unsigned number and then add together. Generally, cast your data type to make sure. Otherwise, you have a lot of fun debugging. So I'm not sure how many circle I should do here, but to be safe, cast your data type, especially if you mix the two data types together. Figure out which data type you want as an output. Otherwise, there will be bugs and there will be long hours where you can't go to sleep because something is wrong with your program. Extension and truncation, again, if you extend, right, from 2 bytes to 4 bytes, for example, the negative sign number extension would work like this. So let's say I want to extend from 1 byte to 2 bytes, right? And I have a negative number. Basically, I can have something like 1, 1, 1, 1, 0, 0, 0, 0, right? This is 1 byte. If I want to actually get the 2 bytes data that have the exact same value as this 1 byte data. The way I can do this is I just add 1. I can keep adding 1 until infinity, and I'll in the 2 complement format, right? This is 2 bytes. In the 2 complements format, if I just extend the MSB bit, the most significant bits with 1, 1, 1, 1, 1, 1, it will still be the same number. It will be still the same number. We don't have a lot of time, so we will do an explanation on why does this work in the next lecture. We don't have a lot of time. And also I kind of need a little bit more room to show you the maths behind it. Truncation will simply just drop, right? If you cut from say 4 bytes, you want to cut it to 2 bytes, you just drop the first to the most significant 2 bytes. So again, circle. The value can change, so be careful. Be careful when you do truncation. Be really, really careful. Right. In summary, extension should be fine. Truncation can change the value, so you want to be careful with your data. We will actually stop here, and in the next lecture, we will talk about the floating point number. But before we end, what is the floating point number? So what is the floating point number? Is a decimal representation, but you can also have quotient, right? Where something like 1.325 is legit. 2.579 is also a legit floating point number. So let me ask you this quick question. Computer doesn't understand these things. How I can convert this to binary? IEEE 754. You are way ahead of the class, but yes, that's why. That's how. But think of before we end the class today, and just like let's do a quick Q&A for assignment 2 and the rest of the in class. Think about now I have this number, right? Where it's 1.325, which is actually basically 1325 over 1000. How can I represent that in binary? And the IEEE 754 dictates that you break the binary number down into 3 parts: the sign bit, the exponent bit, and the mantissa bit. And we'll cover that in the next lecture. And we'll do some example between conversion of binary to floating point and floating point back to binary. So that is actually the end of the lecture today.